You've probably been taught that the most precise machines humans have ever built are atomic clocks. These devices measure time by tracking the vibrations of atoms with astonishing accuracy. They control GPS satellites, global communication networks, and scientific experiments around the world. But here's the contrarian reality. Our most advanced clocks on Earth are not the most precise timekeepers in the universe. In fact, they are being outperformed by the remains of dead stars. Scattered across our galaxy are objects no larger than a city, yet they spin hundreds of times every second with a rhythm so stable that scientists use them as cosmic clocks. These objects are called pulsars, and in 2026, they may be the most reliable clocks humanity has ever discovered. To understand why, we need to start with what happens when a massive star dies. When a star several times heavier than our sun reaches the end of its life, it explodes in a violent event called a supernova. During that explosion, the star's core collapses under its own gravity. What remains is a neutron star. A neutron star is, one of the densest objects in the universe. Imagine compressing a mass greater than our sun into a sphere only about 20 kilometers across. The result is a stellar remnant so dense that, believe it or not, a teaspoon of its material would weigh billions of tons on Earth. But something even stranger happens during the collapse. Because of a principle of physics called conservation of angular momentum, the star begins to spin faster as it shrinks. It's the same effect you see when an ice skater pulls their arms inward and suddenly spins faster. In the case of neutron stars, that spin can become, honestly, pretty extreme. Some rotate dozens of times per second, others rotate hundreds of times every second. These are known as millisecond pulsars. One famous example spins more than 600 times per second, maintaining incredible stability in its rotation. Now, here is where the pulsar is born. Neutron stars also have incredibly powerful magnetic fields. These fields are, trillions of times stronger than Earth's magnetic field. Charged particles accelerate along these magnetic poles and emit intense beams of radiation into space. But the magnetic poles are usually tilted relative to the star's rotation axis. So, as the neutron star spins, these beams sweep across space like the rotating beam of a lighthouse. If Earth happens to lie in the path of that beam, we detect a pulse of radio waves every time the beam sweeps past us. Pulse after pulse, second after second, year after year. And this is what makes pulsars extraordinary. Their rotation is so stable that the interval between pulses can be predicted with incredible accuracy. Some pulsars drift by less than a millionth of a second over an entire year. In other words, a spinning corpse of a star can keep time more reliably than many of the machines we build on Earth. But the story gets even more interesting. Scientists do not just observe a single pulsar, they observe dozens of them scattered across the galaxy. This network of pulsars forms something known as a pulsar timing array. Think of it as a galaxy-scale observatory. Each pulsar acts like a precise ticking clock. By measuring when each pulse arrives on Earth, scientists can detect incredibly small disturbances in space itself, and those disturbances may come from one of the most powerful phenomena in the universe: gravitational waves. Gravitational waves are ripples in space-time predicted by Albert Einstein's theory of general relativity. They are created when massive objects move in extreme ways, such as when two supermassive black holes orbit each other and slowly spiral toward collision. When these ripples pass between Earth and a pulsar, they stretch and compress space slightly. That tiny distortion changes the arrival time of the pulses by just a few billionths of a second, but pulsars are so precise that scientists can detect those tiny shifts. In recent years, international collaborations including Nanograv, the European Pulsar Timing Array, and other global observatories have reported evidence for a background signal of gravitational waves echoing throughout the universe. This signal may come from countless pairs of supermassive black holes merging in distant galaxies. In a sense, pulsars allow scientists to listen to the deep gravitational hum of the cosmos. But pulsars may also guide humanity's future in space. Because their positions and timing are so stable, researchers are developing ways to use pulsars as natural navigation beacons. Just as GPS satellites help airplanes and smartphones determine their position on Earth, pulsars could allow spacecraft to navigate across the solar system and eventually through interstellar space. Unlike GPS satellites, pulsars cannot fail, lose power, or be shut down. They have already been ticking for millions of years, and they will, continue ticking long after human technology disappears. That is the strange reality of our universe. Sometimes the most precise instruments are not built in laboratories, they are forged in cosmic explosions, city-sized remnants of dead stars spinning in the darkness of space, keeping time with a precision that honestly rivals the best clocks humanity has ever created. And every pulse we detect is not just a signal, it is, really, the heartbeat of the universe itself.